Is that good? Let's get started. So we're going to pick up where we left off yesterday. If you remember yesterday, we were talking about dependently typed programming languages, and I was talking about how we might implement a type checker for a very simple dependently typed programming language. And yesterday we worked out some typing rules, and then we discussed how we might turn those typing rules into an algorithm. So on the sides of the boards, and I'm mostly going to be using the screen today, so this is all review on the left and right. These are the rules that we worked out. Now I know if you're sitting over here, you probably can't see that board, and if you're sitting over here, you can't see that board. So I will also remind you that here in the GitHub repository for the lecture materials, all the rules are also in the lecture notes for yesterday. And I've updated these lecture notes so that it covers just what we covered yesterday, including our encoding of product types. And then down here, all of the rules that we developed are also listed down here if you want to refer to them. But what I want to start off talking about today is actually implementing this algorithm. I've given you in this GitHub repository, there are actually several implementations. And what I want to do is start with the simplest one and talk about what the type checker looks like just for these expression forms. All right, so if you've downloaded the branch from GitHub, or if you've accessed the tarball from my webpage, right, the code I want to talk about, it's in the version 1 subdirectory, right? And in this subdirectory, you'll see that there's something that's called source. That's the source code for our type checker, right? And so that's what we're going to start with today, working with this source code. So in this source code, you can see there's a fair amount of code. And for today, we're going to focus on typecheck.hs. This is where the main code for the type checking works. But let me just give you a brief overview of what else is in there. What else goes into turning this from just some scratchings on a whiteboard to a tool that we can play with. So what else do we need to have a type checker? Well, we need to define what the syntax of our language is. We need an abstract syntax. So that is sort of the next most important file in this repository. So syntax.hs, it defines the representation of our unified syntax of types and terms. Right? Typecheck.hs, it also relies on environment.hs. This is what's going to implement Gamma for us. It's going to keep track of our typing assumptions as we run our type checker. It's going to do a lot more than that too, and I'll get to that. What else do we need? Well, we need to be able to read in from a source file, and so the parser, right, reads in, converts the concrete syntax to the abstract syntax, and it uses layout tokens so that we can have layout rules in our parsing. Pretty printer allows us to have nice error messages, prints out the abstract syntax. And modules, that allows us to put our code into separate source files, right? We've been just talking about the expression level, but what is a program? Right? A module is actually a sequence of declarations. If you remember yesterday, we were writing some code, right? It looks like this, right? So we were writing some code in the language that we're implementing. So down here, all these church encodings, right? This is all code that we want to be able to type check, right? And so the overall structure is that it's a module. And we actually I put in some ability to have this module refer to other modules, bring in the definitions there, so you don't have to write everything in the same place. And the other thing to note is in the module itself, it's expecting that for every definition, we're going to first have its type, And then we'll also have what it actually is defined to be. As we extend the language with data types, we'll be able to have more things in our modules as well. Right, so that's modules. And then finally, the last piece of the puzzle is main. This is sort of the top level. This is just the driver that gives us the functions to just run it from GHCI, or there's also, you can run our type checker from the command line. And main puts everything together for us. Okay, so that's kind of the big picture. Now let's look at these implementation in more detail. So what I want to do is I want to look at the abstract syntax, because there's some issues that when you're implementing a type checker, especially for a dependently typed language, you really do have to address right up front, even when you represent the syntax of your language. So I'm looking in version 1, the source files, syntax.hs, and I'm doing it in my Emacs browser just so that we can have the nice colors and edit things. Right, so this is the abstract syntax of our language. And the idea in the abstract syntax is that we want to represent what we were talking about yesterday. Right, we want to represent type, we want to represent variables, lambdas, applications, and pi. Right, and then also the syntax that has some other things in it, and I'll talk about what else is in our abstract syntax in a little bit. But even just thinking about those 5 forms we talked about yesterday, there's this really important question, which is, what about variable binding? Right? How are we going to represent variables, like just regular variables in our program, or variables that are in binding positions, like in a pi type, or over here in a lambda, this lambda binds a variable? How are we going to represent that? Now, we could just use strings as our variables, but that's not what I've done here. So why is it difficult to just use strings for variable binding? Right? What do we need to do? What's important about variable binding? What makes it tricky when we're thinking about a type checker? Yeah? Yeah, so name collision on beta reduction, otherwise known as variable capture when you do substitution, right? You want to make sure that when we implement substitution, it's capture avoiding. If you have an expression with a free variable, you put it inside some kind of binding structure, and if you just happen to use the same name for that bound variable as that free variable, you have a bug in your type checker. Right? So we need to have the capture avoiding substitution. What else do we need to do when we're working with variables, binding variables in some object language? There's another worry, or another thing we just have to deal with. Yeah? Huh? Sorry? Yeah, so alpha is the right word, right? Alpha equivalence, right? We need to be able to decide when 2 expressions are alpha equivalent, right? We notice sometimes we're going to be comparing when 2 things are the same, and we don't want lambda x.x to be different than lambda y.y, right? If we ask the type checker, are these the same function? We want the type checker to say yes, right? We want to work up to alpha equivalence, right? So if we use strings, we can do those things, and it's not too hard, but it's a little bit of work. And so what I'm going to do is there's a library that I have called Unbound, which automates dealing with variable binding for me. Right? And what I'm going to do is if I just use the constructs from this library, it's going to automatically derive capture avoiding substitution and alpha equivalence functions for me. So I don't even have to write them. And if I don't have to write them, then I don't have to worry that I'm getting them wrong. Because they're very subtle, and those are the bugs that are the hardest to find when you're trying to debug your type checker. Oh, the library is called Unbound. So right here, and if you are trying to compile this on your machine, you'll have to install Unbound to have access to it. Right? And Unbound, it uses, I'm not going to really go into the details about how Unbound works, but I'm happy to take questions about it. It uses what's called a locally nameless representation for variable binding. Yeah. Use Haskell's terms already. So you're talking about higher order abstract syntax, right? We can, but it's a little bit awkward to use higher order abstract syntax because a lot of the times we'll be traversing terms. And if you're representing an object function by a Haskell function, it's harder to get access to it. Yeah. Okay, so in Unbound, there's a couple of type constructors that I'm going to be using that's going to make it all work. Right? So the first one is name, right? And this is just saying that I'm defining this new type tname, and tname is just an abbreviation for a name for a term. This is the type that I'm going to be using to represent variables. So down here, variables, right? My var constructor of my data type, it takes a tname, a name for a term. And the nice thing about having that name type indexed by the data type that it lives in is I can't confuse these variables with any other kinds of variables. If I was working in another language where I had term variables and type variables and coercion variables and whatnot, I wouldn't want to get them confused. I would want to make sure that I didn't mix up which variables were which. Now in this language, we only have one kind of variable, so it's less important. Right? So we're using the names from Unbound, and then the next thing we're using is we're saying that lambda and pi are binding structures. And in fact, they bind variables inside some other term. Right? So lambda is going to bind this name in the term, pi will bind this name inside that term. Now bind actually takes a pattern. It doesn't just have to bind a single variable. It can bind many variables, and in that pattern, it doesn't have to bind every variable that occurs in a pattern. That pattern can have some type signatures inside of it. So an embedded type signature in the pattern, that's just called an embed. So here in pi, we're saying we're going to bind this pattern in this term, but that's only going to bind this name because this term here, that corresponds to the A in our pi type. It's just embedded. It's just along for the ride. But it allows, I don't have to do it this way, but I'm demonstrating something that if you wanted to go use Unbound in your own language, you're probably going to start getting more complicated binding structures. So I wanted to give you an example of how embeddings work. And the same is true for lambda. So if you remember last time, we only worked with lambdas without any sort of annotation on the type of the binder, right? Lambda x dot a, not lambda x colon, here's the type of x, right? But having that type there, giving somebody the opportunity to write that type down, that allows you to type check lambdas even in inference mode. So for flexibility, we're going to allow an optional type annotation. So a type annotation, it's just an optional type. Down here, a type annotation, maybe there's some type there, maybe not. So we'll put that with the binding variable for lambda expressions. Right? And that's it. So just using bind, embed, and name, that's all we need to do to get substitution and alpha equivalence. Down here at the bottom of the file, these are some of the instructions to Unbound to say that we want to generate alpha equivalence and substitution functions, and also, I didn't mention this before, free variable calculation functions for these data structures. Right? So the first part here, derive, that's telling Unbound to derive some sort of representation of these type structures that it can work with. And then here, alpha, this is making these two functions available for the term type, right, based on that structure representation that it derived. So since we have this line right here, we can now call the alpha equivalence function on anything, on any term, and it will tell us whether two terms are equal up to alpha equivalence. Or we could call the free variable function, and it will give us all of the terms that are, all of the names that are free within that term automatically. We don't have to write this code. Right? And substitution is slightly more, a little bit trickier, because you have to say what you're substituting into what, and you have to identify where the variables are when you substitute. So the class for substitution, it's going to give us actually single and multiple substitutions, but look at the type of subst, right? We don't necessarily have to substitute just terms and terms. Maybe in some other time we might be substituting, well, actually here in this example, we're going to also be substituting terms inside annotations. Annot is just another type I defined. We're using it with our term data structure, but we want the substitution to continue through it. Right? So we'll be able to substitute terms and annotations, terms and terms. The type of substitution makes sure that we can only produce things that make sense, that we can only substitute for term variables inside of a term. Right? These two lines here will only type check if x happens to be a term variable, right? Because we're substituting within a term. And we've identified this as a variable we want to substitute for. Otherwise, it would leave it alone. Right? So this automatic generation of substitution functions, it's making sure that we're avoiding variable capture automatically. And it's also making sure we're not confusing if we have different sorts of variables. If we have coercion variables, type variables, kind variables, term variables, it makes sure that we keep them straight and we don't confuse our substitutions. So this is a little bit of extra help that we can get. Now, what else? Let me just see if there's, I want to talk a little, before I switch to talking about the type checker, I want to say a few more words about what else is in this file, what else is in this syntax. So I have a couple of things that are there just for, we're implementing a type checker and we'd like it to be nice to us, i.e. we'd like it to be able to give us error messages that we can use. So in our syntax, we're actually keeping track of source positions, right? And the parser will automatically put those source positions buried into our syntax. And our environment, when we're working with our context, it will keep track of the closest enclosing source position. So that's going to allow us, when we do an error message, that it'll actually tell us where the type error was, not just your code doesn't type check, reject. Another thing we have, paren is just to help out for pretty printing. And that is, remember we talked about having a general form of type annotation, allowing somebody to say, this expression has this type if we want to go between checking mode and inference mode. So we have and for annotations. And then the last one here that I'm going to talk about is trust me. This is another hack, right? But this is allowing us to turn the type checker off, right? When you're working with a dependently typed language, there's going to be times when you want to incrementally build up your terms. And you don't want to have to write down everything at once. You want to just, in AGDA, you're going to see you're going to leave a hole. In Calc, you can skip you could skip one of your goals. Here in Pi for All, trust me is a special term that has any type that you want it, right? You have to say what type it has. That's why it has an annotation on it. But if you just want to say, I'm not done with my term, I'm just going to put a hole there, that's what trust me is for. And you'll see in your homework assignments, I've made up some homework assignments for you for practicing learning about Pi for All by writing some Pi for All code. What I did is I put some trust me's in, and then you can go through and fill out those trust me's with the actual definitions that make sense there. Okay, any questions about this syntax? Especially, I know Unbound is a little bit unfamiliar, but you'll see that actually you'll see that we don't really have to do much. Things just are going to happen for free for us because we have unbound available for us. Okay, so let's go to the type checker, right? And remember, we want to implement these two judgments, the checking judgment and the inference judgment. So what does that mean, right? What does that mean for the type checker? It means that we want to implement two different functions, a function that infers types and a function that checks types. So let me just go to a Scratch page. So I'm going to make the font just a little bit bigger. All right, so we want to write Haskell code that looks like this, right? Infer type, right? And infer type, we want to, right, give it a term and some sort of context, and maybe it will give us its type. And check type, give it a term and a context, and maybe it actually bool, right? It tells you whether that, and a type, right? It tells you whether that term in that context has that type. Right? Does this make sense? This is kind of what we want. This is sort of the most direct analog to the functions that we were talking about, that we're trying to develop. And remember, term and type, I wrote type here and I wrote term here, but they're really the same thing, right? Type is just an abbreviation for term. But this is not what if you go look at type check, this is not the types of the functions in that file, right? And the reason is, well, there's a couple of reasons, and I want to go through those reasons right now. So the first thing has to do with this bidirectionality, right? The thing about bidirectionality, we broke our typing judgment up in these two pieces, but note that it's not exactly closed under substitution. What do I mean by that? If you think about the app rule, right? You think about the app rule here. We're going to be substituting this b, the argument b, for x in capital B, right? And we want to make sure that after we do that substitution, we get something that still type checks. But what happened? When we checked B, if at some time we checked B and verified that it was a well-formed type, that variable x, it was checked in inference mode. We could infer the type of that variable. But the argument B here, we checked it. We knew its type when we started running the type checker on it. And so we're going to potentially be putting it in this context where we don't know that type that it should have. And so after that substitution, we may not be able to just run our check type or infer type and find out that this is well formed. We might be mixing up the modes after doing that substitution. And so that we don't have to deal with, now we could define substitution so that it tags it or something like that, but for simplicity, what I'm going to do actually is make our type checker so that it gives us a little bit more information. It gives us an elaborated term, and that elaborated term is something that has all the types that are missing. It has enough annotations that we could always run inference on it, right? Something that we don't need to have this bidirectionality for it. The bidirectionality is going to help us for source terms. It's going to make sure that we don't have to write down that many annotations in the object language that we're type checking. But once we've figured out that something type checks, we can just stick in those types into our abstract syntax, into the annotations, and then always be able to run the inference mode on it. And so what that means is infer type and check type, they're going to give us actually two results. Well, infer type will give us two results. It's going to give us the type of the term, but it's also going to give an elaborated version of the term where annotations have been filled in. It just has more type information for us. And check type, it's going to give us, if it succeeds, it will give us the elaborated version of the term. So that's the first change from what we talked about last time. We want to do a little bit of elaboration. We're going to be propagating type information around locally. Let's stick it in the term so we always have access for it.
Again, what you mean by an elaborated term?
Okay, so for example, right, we might write in the source code, we have ID, lambda x.x, right, and actually it'll just be the Boolean ID. Bool, arrow bool, right, ID bool is this, right, and you can, but if you look at it, right, you need to know what context you're checking it to know what type that is. And what check type is going to do is it's going to take this term and that type, and it's going to produce a type that we don't need to have, or it's going to produce a new term that we don't need to have the type around to know what its type is, that we can always infer its type. So it will produce the annotated version that looks like that.
So basically, you're going to eliminate all type signatures from...
Yeah, we're going to eliminate the need for checking mode, right, by providing type annotations in our term so that our standard syntax-directed inference mode will always work. Right. In this simple language, there's only two annotations that elaboration is going to add. So the first one is right here on lambdas. It's going to annotate the domain type. The other one is trust me, right? If you have a trust me, right? So say we had something and we didn't actually feel like writing the identity function for bool yet. We just said trust me, right? What's the type of the trust me term? In this context, because we put a type signature there, we know that it should have type bool arrow bool. But what we're going to do with the elaborator is we're actually going to annotate that type onto the term so by itself we always know what the type of that term is. That's another example where elaboration will add a type to the syntax. Yes?
What's going to happen if we pass one of these annotated elaborated terms into the inference library?
So we will make sure that when we write our code for inference mode that if there are annotations there, that it will make sense. It will use them and make sure that they are correct annotations.
And what if, as a programmer, I'm providing annotations?
Yeah, so you should be able to provide all the annotations that you like, and our type checker should make sure that if you wrote the wrong annotations down, you should get a type error.
So in that instance, we're actually using checking, not inference.
Yeah, yeah. Yes?
By sort of mixing up inference and checking mode and how that might happen when you're substituting?
Okay, yeah, so this motivation here. So here I'll rewrite the app rule up on the screen in case some people over here can't see. Right, so if you remember in the app rule, right, we infer the type of the function and we check the type of the argument against whatever the domain type of the function was. Right? And then that allows us to infer the type of the application, which is a substitution B for X. Right? And now what I want to focus in is think about this type. Right? When we infer a type, we want to make sure it's something that our type checker likes. Right? And so if we were to somewhere say, if we inferred that type, it's going to be sort of a meta property of our type checker, that it should also be that we could check that that phi type is a real type. Right? That should succeed. If we call our type checker on the phi type, it should work. Right? And to make sure that happens, we also want to make sure that if we call our type checker on the result type, it also succeeds. But here, that may not happen. And the reason it may not happen is if you think about this one. When you're type checking B, there's some X in there. And it's a variable. And variables in our type system are checked with inference mode. We can infer the type of the variable. Whatever context that variable appears in, it doesn't need to know what the type to expect for that variable. Because we can look it up from the context. But down here in the substitution, this B, it got a little extra help when we were just checking to make sure that B was a good term. Right? Because here in the judgment, So this is where we're at. So those were examples, but this is where we're at in terms of the type of our type checker, right? And there's a few more. This is still not quite the type that the type checker has in the implementation, right? So a few more changes, and the next changes are, let's think about how we're using this context. So is anybody familiar with the reader monad if you're a Haskell programmer, right? Yeah, right? Or it's also called the environment monad, right? And what does it do, right? If you notice this type here, right, we could kind of put this into a monad. We could write our type checker and make it a monadic type checker and let the type checking monad keep track of that context for us. We don't need to do it explicitly. We'll let the monad do it, right? And the same is true for maybe. You know, maybe is also a monad. And actually, it's not a very good monad for our type checker, right? Because what happens if our code doesn't type check? It just returns nothing, right? But we'd rather that it return an error message. So instead of using maybe, perhaps we should use an error monad for our type checker, so that when something goes wrong, our type checker can give us an informative message, including that source position, about what went wrong in the type checker, right? And so what the environment.hs file does is it defines something that's called the type checking monad, right? TC monad, and that is going to take care of both the context argument and the maybe argument and internalize them, right? So really, let's see here. We need that type still. Right? Right? So that TC monad, it's going to incorporate both passing that context around and dealing with error messages. And it also will give us another place to stick extra information if we need that during type checking. What other information might we need? Well, when we're dealing with variable binding, once we start traversing these terms, whenever we get to a variable binder, we're going to want to generate fresh variable names when we open it. So TC monad is also going to include some functionality for generating fresh variable names. That functionality we inherit it directly from Unbound, and you can look at the environment file for more information, but it's also going to allow us to be sure that when we're working underneath some binding structure, whatever name for that bound variable is, it's a unique name. It's not going to collide with anything else. Okay. And then let's go take a look at type check. There's one more change. We're really close. So here's infer type, and here's type and check type. To make their types a little bit more, check type also gives you back the term the type that you passed in, so that both infer type and check type are going to give us the elaborated term and its type as its result if it succeeds, right? But if you look at this code a little bit more closely, you'll see that they're actually both defined in terms of the same function, TC term, right? What's really difference between infer type and check type is whether we have this type available, right? And sometimes it might be useful to do the same thing no matter whether we have that type available or not. So we can combine these both into the same function by just having a maybe here, optionally passing in. If we pass in a type, we're in checking mode. If we don't pass in a type, we're in inference mode. Right? So really, the real function that we're going to be working with right here, it's TC term, our type checker, right? That takes a term, maybe takes in its type, and working in this monad is going to elaborate that term and tell us what its type is. Right? So this is the heart of our type checker right here. Right? And this is the code that we want to extend to implement all of these rules. Okay. Now, in the version that you downloaded, if you downloaded that, it's all filled. Actually, many of these things are filled in. I took them out so that we could work through exactly how the connection between how these rules are written on the whiteboard and how we're going to implement them in Haskell. Now, was there a question? Okay, yeah. Yeah. I'm not going to teach you monads in one sentence. All I can tell you is don't read any monad tutorials.
Monads are not.
The best way to learn about monads is to learn about them through examples. Right. Now you're going to see, I'm going to be showing you an example of a monad in action. And it's a kind of a complicated monad in action. But later, maybe during the hands-on session, come talk to me and I'll show you a much simpler example. Right. And a couple of them. And so you can kind of get a better feel for them. Yeah, you'll also be able to find other people who can show you examples. But my personal philosophy is don't try to understand them as a general concept right up front, right? Just understand each individual example first, and then you'll be better able to get the big picture. Yeah? Yeah. Oh, you're right. I wrote that on the board wrong. We're inferring that type. We can't check it. Right? I should have written it the other way. Yeah. Okay. So, we have our type checker, and just to prove to you that it doesn't work, right? So we have this file. This is going to be our test file. And our goal in the next couple of minutes is to get this file to type check. Right? So that means that we have to go to our type checker and do enough of these cases so that the code in the file works. Right? And we can see whether we've got it to work right here. I'm in the directory, actually, I'm in the directory for so the directory I'm in it's in version 1 source, is the directory I'm in, and I'm just telling GHCI to load the top level, right? So it loads and compiles everything. And then if I want to run the type checker on a file, I have the main.hs, it has a function called go file name. Run the type checker on this file name. And we're going to say go to the file in the test directory called lec1.py and run the type checker on it. Right? Now this shouldn't work because you just saw that the type checker has a bunch of holes in it. Right? So and you can see we get a type error. Right? It says our type error says unimplemented pi because we haven't implemented the pi case when we're type checking this particular type. Right? And even nicely, we can click on this. Here's our source location, and it'll take us right down here. So what happens? What's going on when we type check this file? Well, the first thing it does is it wants to check this term in checking mode, but it doesn't want to use just any arbitrary type. It wants to first make sure that the type that you wrote down for it, for this term, is a good type. So the very first thing it's going to do is make sure that this thing right here is a type. So that's why pi is the very first thing that it's looking for. It wants to know, how do I type check this pi type, right? And notice that it's printing it out slightly different than how I wrote it here, right? And what's the difference? Well, x doesn't appear in the range type in the code of the pi, and so it's using the more standard arrow notation, right? Those two types are equivalent to each other. Yeah.
So my loading doesn't work because I have some modules missing. How do I load them again?
You have some modules. It can't find the modules?
Yeah.
I think you need to make sure that you're in the source directory.
Okay.
Right. If you just try to, sometimes when you just try to load it from using the Emacs mode, it will put you in the wrong directory. Or is it the unbound modules that it can't find? If it's that, you need to use Cabal to install the unbound modules. Yeah. Yeah. Okay. So let's implement pi, right? So that we can at least check that that type works, right? So down here, let's go. Pi is our first error, right? So how do we make sure that a pi type is well formed, right? We are doing this rule right here, right? So what does that mean? So pi is a little tricky because it actually binds a variable. And so the very first thing we have to do is ask unbound to take apart that binding for us. And we can do that using something that looks like this. So what does this mean? Unbind, bind. So binding is this sort of bind, BND, is an abstract thing that we can't have access to it until we ask unbound to take it apart and give us this components. And by asking unbound to do that, unbound can ensure that we have a fresh variable name for x. So it's giving us x, it's giving us that embedded type, and then it's for the A component of the pi type, and then it's also giving us B, the B component, and making sure that all the variables use the same name, x, that we just made sure was fresh. Right? So that gives us access to the components of that pi type. And what do we want to do with those components? Yeah?
What does the right arrow do?
Oh, this is a monad thing. Oh, this one, this arrow. This is making dealing with that embed a little bit easier. It's called a view pattern, right? And it's in the pattern allowing me to take apart that embedding right away.
The view pattern basically runs the function on the left of the arrow before binding the result rather than binding directly. So in this case, you're pattern matching the tuple, and instead of actually pattern matching the tuple, it will first run an embed on the thing and then give it the name.
Okay, we want to check A, right? So we're going to call the type checker on A, and we want to make sure that it is a type. And what is the result? The type checker is going to get an elaborated version of A, and its type, which we're pretty sure is going to be type, right? And that should be, that's this first line of the rule. Right? And notice I didn't have to write the context down. I didn't have to say anything about gamma because the monad is keeping track of the context for us. The fact that both of these functions are in the same monad, it's using the current gamma. Now, the next line, we want to also do the same thing for B, right? We want to elaborate it and check its type, right? Make sure that it is also a well-formed type. But we can't just do this, right? Because we want to, when we check B, B could have some x's in it. So we need to extend that context to tell it about x and to tell it that x has type A. And so in the environment module, there's a function specifically for extending context. So let me just make sure I write it down. It's called extend context. And what it takes is it takes a declaration that says that the type of A is, or the type of X is elaborate A. Right? So what this does is that extend context with the type of X that goes into the monad, changes our context so it now includes this new binding of X for A. Yes?
Looking through the code, I don't see anywhere you ever use the second number of the tuple returned by check type.
You mean you're looking at some of the full things, or?
Well, looking at typecheck.hs, what I'm asking is check type ever going to return you a type that's different than the type you passed in?
I'm not sure. Not in this version, but when we add more things to this language, it might return something different. Okay. So now the next thing we need to do is return the answer, right? So we've checked the two things. If we get to this point, they've succeeded. If we don't get to this point here, there was some type error, and our code, our monad has reported that error. But if we get to this point, there are no errors. We've checked those two things. And so now we just need to say, okay, we're going to return our elaborated pi and its type, right? So its type is type. And the elaborated pi, we're going to use these two components, LA and LB, that we got from check type. So we'll bind X embedded with LA and LB. And that's going to put it together to create the binding that pi expects. That re-wraps it up for unbound. Okay. Let me just make sure I didn't have any typos there. Go back, put it back so you can see it. Let's reload main.hs, which will recompile this file. Okay, so the Haskell type checker likes our code. Should we run it now on our test file on lec1.py? Is it going to work? What's going to, just to remind you, what will be our next error message? Clearly, we've only done one case, so we're not going to be able to type check the whole file. Where's it going to get stuck next? Let's see. So I'll go rerun it on lec1, right? And now it says, oh, type, right? So why does that make sense? Well, we just said, here's how to type check the pi, but then our first line was, now make sure that the A portion, the domain type of the pi type, was well formed. Now we need a case for this type, right? And that's exactly where our error message is pointing us to. So we need to go over here and add this case. Now, what is this case? Is this easy? What is it?
Type and type X.
Yeah, right? It elaborates to itself, and its type is type, right? Because that's this rule right here. We're using the type and type axiom in this. If we were to stratify it, we'd bump up the level one. Okay, so that's the next step, and we'll run that again, reload it, and then see if we get any further. Right, now we have a variable. That's this variable here. So we started doing this pi type, but we know how to do pi types, so now we're doing this variable. So let's go add the variable case. All right, and here we're going to access our monad, which is keeping track of the context, and ask that monad, do we have a binding for this variable in the context? All right, so we look up the type of that variable. So does X have a variable or a type in that context? And if it succeeds, it's going to tell us what the type of that variable is. If X is not bound in that context, if we don't have an assumption for X, it's going to give us an error message. Right? And then we can return var. We don't need to elaborate variables to anything new, but we can return it and its type. Okay, so let's check that, run it. Right. So we finished the type. Our next error message says, now I don't know how to deal with your lambda expression. All right, so we've got as far as making sure that this is a well-formed type. Okay, so how should I do a lambda expression? Right, so here, this is the case that we got our error. What do we need to do? And this is a little bit trickier, right, because we're checking a lambda against some pi type. And what happens in the rule here? Right? Notice there's a really funny thing in this rule. Right? We have an x here and an x here, and they're both binding x's. Right? And when we wrote the rule down, normally when we think of binding variables, we assume that they are different from every other binding variable. But here, I wrote down the same x. And it's important that they're the same x, because right, when we do our recursive call to our type checker, we want the x's in A to be identified with the x's in B, right? And so what we're going to do is when we open this up, we want to make sure that Unbound uses the exact same variable name for, it's going to generate a fresh name, but it's going to be the same fresh name for both the body of the lambda and also the result type of the type, right? And so here we have to use yet another thing from Unbound. It's called unbind 2+. It takes two binders and make sure that their variables line up, right? So that'll give us x, right? So, well, we don't really care about the. I'm just going to skip the annotation for now. And we know we're going to get x again. And let's see here. That x again. And then we're going to get embed y. Oh, I forgot the body. The body of the lambda. And the result type of the pi type. So what are these four results we get from unbind 2+? Right? We get the binder for lambda, that's x, and for right now I'm ignoring any annotation that might be there. Then we get its body. Then we get the binder for the pi type, which has a variable, which we know is already going to be x, and its annotation, which is the domain type of the pi, and then we also have its body, which is the range type. So that's how we can get access to all of those components. But again, it happens automatically. X is going to be a fresh variable, but body and type B are going to automatically have references to that fresh variable x that Unbound just generated for us. Okay? What next? How do we type check a lambda? What do we need to do to make sure that this lambda expression is well formed? What does this rule say, right? When we're checking a lambda against some type, we need to check the body of the lambda against the result type in an extended context. So we will do that, right? We will check the body of the lambda against the result type, but we need to extend the context, right, with a binding for that variable with the argument type. And what is that going to give us? That's going to give us an elaborated body, right, and a new type B, which I'll just ignore. Okay, so that is going to make sure that that body of the lambda type checks. And then as a result, we'll just, that's all we need to do to produce a new elaborated lambda. We just need to bind our elaborated body back together. Let's see, we'll name that with the same annotation that we had. And its type, well, the type of it is the same type that was passed in. Let's make sure I got that correct. All right, now let's try to run that and see if it can type check our identity function now. Right, great. We got further, right, because our next error message says that I don't know how to deal with applications. So that meant we were able to check the entire identity function example. Yes. Yeah. Yeah, so I was doing the most simple thing for this particular case, right? We can't ignore that type annotation forever. We should go back to this code and check that annotation and make sure it is the same as the type that the pi gave us, if it is present. I'm not going to do that now just for time, but if you look at version 2, that's exactly what it does. Okay, so we just have, the only thing we have left, so I also did the case where we don't have an annotation, but we do have, we're not in checking mode, we're in inference mode for lambdas, but we do have an annotation. I've already done that case for us. Right, so the only case that we have left is this application case. So let's just do that, and then we will have a complete type checker for this simple language. Okay, so how are we going to do this type checking for the application case? Again, we're implementing this rule here for application, right? We don't know the type, we're in inference mode, but how are we going to figure out what the type is? By making recursive calls to our type checker. What do we need to do first? Yeah, so we need to infer the type of the argument, T1, or the function, T1, right? Infer type. And that is going to give us an elaborated version of T1 and some type of it. Okay? What next? Well, we need to look at that type, right? Right? We inferred the type of that function. But we need to make sure that that type actually is a pi type. So let's use pattern matching to look at it. All right, so maybe it's some pi type, or maybe it's not. All right, so if it's not, we just want to give an error message, right? Function, and we can give a little error message that tell us that this function should have a function type, instead has type 1. Right? We can explain what's going wrong. These DSs and VDs, those are instructions to the pretty printer. The pretty printer knows how to print out expressions, so DD says print out the string of this expression. And it allows us to put together concisely error messages. Okay, so, but if we don't need to do an error message, if it is some sort of pi type, we need to, again, unbind that pi type, unembed type A, type B, unbind, bind, right? So that gives us access to the components of the pi type. And then what? Then what do we want to do now that we know what type A and type B are? We want to check the type of the argument to the function. Check type T2 using the type that we got from the pi. And that is going to give us an elaborated argument and some type that's probably going to be the same as A. Now what? Now we've inferred the type of the function, checked the type of the argument. Now we can return the result. If we get to this point, everything looks good. We can return our elaborated term. And then we also need to return its type. Right? And for that we have substitution. Right? We're going to take x and replace it with the elaborated argument inside of type B. And that call to subst is going to do the substitution for us. And by using the elaborated version of B, we know that it'll always work in inference mode. So let's check that. So Reload. Okay. Let's see if we can get further along in our examples that we worked out yesterday. Right? And we did. We got all the way down to line 34, but we didn't finish. Why didn't we finish? Well, down here. So we finished ID, we did some examples of applications of IDs. Here's some church encoding of Boolean, which I didn't really talk about, but I stuck it in the file anyway. Here's our church encoding of and our error message goes down here, right here. It's when our definition of proj1 somehow didn't work. Right? It says function A should have a function type, instead has type and PQ. We need to unfold and. Right? Where? How? Why? Right? Here's our rules. They don't talk about unfolding anything. Right? What's going on? Yeah. So what comparison? Where are we doing a comparison? Right?
Whenever you insist on the type when you rule, so X bet A B, that's a comparison.
Right here, this one right here. So here we're doing a comparison, right? We're implicitly, remember what happened. We inferred the type, and then we just pattern matched it, right? So that said that whatever type we inferred had to exactly be a pi type. It couldn't unfold, right? We had made a definition that when you expanded that definition, and what is expanding a definition? That's beta reduction, really, right? In this case, especially and takes two arguments. When it reduces, it's something that reduces to a pi type. It's not directly a pi type. It's something that reduces to a pi type. So actually our rules that we wrote on the board aren't quite expressive enough. And the reason that they aren't expressive enough is they're too restrictive when it comes to equality, right? Here we're expecting, it actually has to be a pi type, not something that's equal to some pi type, where equal means not just alpha equivalence, but beta equivalence as well. So it allows us to unfold these definitions. And here's another example right here, where we have an equivalence in our typing rule, where we switch from checking mode to inference mode. Right now, if you look at the code in the type checker, I just made the type checker just ask for alpha equivalence. Right here. This is the line, it's the last line that switches. It says, you gave me a type, but I didn't have any cases in my pattern match that worked for checking mode for this term. So maybe I should switch and get rid of the type and try to call the type checker again without that type, which is going to enable all of the inference mode cases, and then compare the results. Right? So for checking, we have a type, we get to this point, we do infer type, find out what that type is, and here we say, well, okay, make sure that those two types are alpha equivalent. That's the equivalence that we're using in this type checker. Make sure that they are the same, right? Of course we're going to do alpha equivalence. We don't want things that differ only in binding variables to be different, but we actually want something stronger. We want a version of equivalence that's going to equate more expressions, more terms than that. Yeah? Oh. So what this line means is that unless takes a Boolean value, right, and it works with a monad that's an error monad, right, and if this evaluates to false, then it's going to throw this error. If it evaluates to true, it does nothing. It just goes on, continues to the next line. Right. Okay. So what happened was We developed a language last time, but we didn't finish the job, right? Our definition of what equality meant, our definitional equality for this language was not as much as we want it to be, right? Even the examples that we worked out, we still can't check them because we think that and PQ, right? Here, let me go back to our example. We think that and PQ should be identified with this type. If we know what P and Q are, we should be able to reduce and PQ to this pi type. That's what we said it was. But our type checker didn't know that. All right, so now I kind of want to switch gears again and talk about what the definition of equality really should be and how we implement that in our type checker, where we need to change our rules, and actually how we need to change, we need to create some kind of new function to replace alpha equivalence and to replace that pattern match in the application case. How are we going to implement that function? Okay. How are we doing on time? Yeah.
So if we're going to allow rate of reduction in our type checking
Yeah.
process, don't we introduce the possibility of not being able to type check for the term?
What you're worried about is that I said before that we're not doing anything to rule out infinite loops, right? And so that means that our definition of equality, if it includes beta reduction, it's going to be undecidable, right? Because two things are going to be equal to each other if there's some common beta reduct. And how do we know whether two things, right? We might have to solve the halting problem to decide that. That is true, right? That's a consequence of this utter cheat I'm doing by not enforcing termination. On the other hand, so that's going to mean that in some situations our type checker could go into an infinite loop. But even if we went and we enforced all of that, we made sure that everything everything terminates like Cock and Agda do, that still doesn't tell us that our type checker is going to finish in any reasonable amount of time, right? We can still, type checking is going to include beta reduction, and so we're still going to have to be doing these beta reductions while we type check. And we could write functions that do terminate but take a long time to terminate. And if our type checker decides it needs to reduce it to its final form, it could take an arbitrary amount of time. Right? So yes, it would be better to know that our type checker always terminates, but we're never going to be able to have any guarantee that our type checker will be fast, for example, because our language is so expressive. We can essentially, by having expressions in types, we're kind of programming our type checker, and we have a lot of flexibility in that. Right, and you may notice when you're programming in Cock or Agda that if you add a lot of expressions inside of your types, type checking can get slow. Okay, we need to define equality, but we have about 10 minutes. So before we do that, I forgot last time to talk about homework, right? And so, but I did have some made up, so let me just quickly go over some things that you can do during the hands-on session this afternoon if you want to have some more experience with this. And I actually have several kinds of homework based on if you're familiar with Haskell and want to play around with the type checker, or if you're not familiar with Haskell and you want to play around with the object language that we're writing. Right? So if you are familiar with Haskell, if you look at this code, you'll notice that there's a lot more here, right? So I put in some syntax for Booleans, right? So a Boolean type, Boolean values, and an if expression. And I also put in some syntax for sigma types, dependent products, right? The type of sigma types, an introduction form for sigma types, and a case analysis for sigma types. So, and in the notes, over here, if we go over to, let's see if I am still, yes, good. In the first set of notes at the very bottom, I have some typing rules for Booleans and for, oh, they're now, I moved them to the second one because we're doing them today. Right, I have some typing rules for Booleans, and I have some typing rules for sigma types. And those typing rules will also show you the concrete syntax in Pi for all for sigma types and for Booleans. And what your job is it's two parts. The first part is to think about, so these I just wrote as normal typing rules. They're not bidirectional. What would the bidirectional rules look like for these constructs? What's the bidirectional? How do you turn these rules, these are not an algorithm, how do you turn them into an algorithm? All right, so that's the first part, is to sit there and think about how to make them syntax directed. Right? That's first. The second part, if you're familiar with Haskell, go to the version 1 code, in version 1, the source type check code, and see if you can implement those rules that you've thought about. Right? And I have in test homework1.py, I have some test cases for you. So if you want to see whether you got something, if your type checker works, you could try it against this file. So that's the first bit of homework. So even if you're not so great with Haskell, you can think about the bidirectional rules. And then the second bit of homework, let's see, where did I put it? If you go into version 2, in version 2 contains the answer to this homework. You could also look at how I implemented the type checker for if and sigma types, right? And so if you compile that, you'll get a full-fledged type checker. If you wanted to play around with church encodings some more, I have a test case for church encoding of natural numbers. I know a lot of people were interested and hadn't seen church encoding and wanted some more practice with church encodings. So here is a church encoding of natural numbers, but down here there's some trust me's in it, right? And then it also shows you that since we are working in this language that doesn't necessarily terminate, we actually can do another kind of encoding called a Scott encoding, and it also walks you through that as well. So if you want some more practice with encoding things, do this, but you need to run this test with the more complete version of the type checker, because you need to have the equality all worked out. Okay, so that's 2 bits of homework, right? Think about extending the type checker with Booleans and sigma types, and play around with church encodings. Okay, so in the last 5 minutes, let's just set up thinking about definitional equality a little bit more, and that's where I'll pick up next time. Right, so we're going to do a definitional equality, and at this point I'm just going to ask you, what do you think should go in that definitional equality? How are we going to define it? Right, you said it should have beta equivalence, right? But what else? Right, really what we want to do is we're going to define a judgment for when things are equal. What should go in that judgment? Right? How do we say when things are equal? So I'm going to give me some more board space, right, by raising the screen. Wake up. And see if that works. Yeah. And tell me, what should it mean, right? When we write A equals B, what are some rules that we should go when we define equality, right? So containing beta reduction, that just means we have a rule that looks like this. If we have an application of a lambda to an argument, that must be equal to the substitution. Take the body, substitute the argument for x inside of it. Are we done? Do we need more? Yeah. It should be a congruence, yeah. Yeah, so first you said the three things for an equivalence relation. So let's think about the rules for that. So we want to make sure that it's an equivalence relation, right? Reflexivity. A should always be equal to A. Symmetry. A equals B, B equals A. Transitivity, right? A equals B, B equals C, A equals C, right? And then what else did you say for a congruence? What else do we need to actually take this equivalence relation and make it a congruence? Yeah. So we need to look at our different forms of syntax, and to make this a congruence, that just says if the subcomponents are equal, then the entire thing should be equal. So the congruence rule for lambda looks something like this, right? Two lambda expressions should be equal if their bodies are equal, right? This is a congruence rule for lambda. And we're going to have another congruence rule for pi types, right? So we have two pi types. They should be equal when the domains are equal and the ranges are equal. Yeah, now you're really sensitive to variable names, right? Here, they're binders, I'm calling them the same variable name, right? So that means that A and B are going to have x's in it, and it's going to be the same x. And so in here, we're just going to be looking for the same x. Okay, so what about alpha equivalence? Yeah, here I'm doing this. When you read type theory papers, they often write the papers up to alpha equivalence, and they just do it completely implicitly. And it's kind of annoying in a way, right? Where every time you write a term down, it's kind of up to alpha equivalence. So if there is a way to alpha vary these two lambdas so that they have the same names for the bound, you're allowed to do it. Right? So this rule would also allow you to equate lambda x dot x with lambda y dot y, right? Because implicitly we can alpha vary the terms. Yeah, when we implement this, we're going to have to be very aware of that, right? And when we go over, if we're trying to compare these two things, right, we'll need to use that unbind 2 to make sure that it'll produce the same name for the two things. Yeah.
Was the unbind 2 plus or
yeah.
Did that fail if they were different, or did it just kind of unify them in a way?
It made sure that they were the same, right? It's not going to fail because the name, with alpha equivalence, it could be any bound variable that makes them. So it'll make sure that it can make them the same. Right? And I'm glossing over how it actually works. Underneath the covers, there's no names, right? So it can't fail. Okay. Did I get all the congruence rules? Are there any more? Yeah?
Yeah, definitely application.
Application, yes. So we also need one more for application. All right. When A equals B prime, B equals B prime. Anything else? There, we would probably have to add more congruence rules for if, right? But we won't do that right now. And then we also want to make sure that this is true. And I'm going to add the rule, but then we'll have to talk about later how we implement this rule and whether it even follows from the other rules that we've already said, right? And what this is just a property that we want to hold, that we want our equivalence to have this idea of functionality, right, that says that if we have two things that are equal to each other, then in any context that they might appear, those larger terms will still be equal, right? That if A1 is equal to A2, then we can take B and put it in anywhere inside of B. If we put A1 there, that's going to be equal to having B with A2 there, right? Knowing this is true will also help us later when we start reasoning about equality. Okay, so I'm going to end here, but I'm going to also give you the task, because this is just a thinking task. We're defining equality with these rules. How do we implement this? Right? We want to write a function that when given two terms either says yes, they are equal to each other according to this relation, they're in this relation, or says no, they're not equal to each other, gives an error message. How do we implement that? Okay?
Thank you.
Thank you.